Hello there and welcome to Physics with William, where science takes us on explorations to unravel the wonders of the universe. As always, we set out to dive into complex questions, searching for answers that may reshape our understanding of reality itself. Today we embark on a journey into the very fabric of time, space, and the limits of the physical universe. We're going to explore a concept that has fascinated physicists and captured the imagination of many: tachyons. These particles, which exist in the realm of theoretical physics, are thought to break the speed limit of the universe, defying what we know about the laws of nature. To begin, let's take a step back and consider something we all know well: the speed of light. For most of us, light seems to have always been the fastest thing in the universe. A beam of light, no matter where you are or how far you travel, always seems to travel at the same speed. It's the ultimate speed limit, firmly etched in our understanding of how the world works. The notion that something could surpass this speed feels as outlandish as it sounds. After all, how can you move faster than something that already feels like it's as fast as it gets? But that's where tachyons come in. These elusive particles, while still purely theoretical, have been proposed to break that boundary, suggesting that the universe isn't quite as simple as it seems. Before we dive deep into tachyons, I want to ask you something. What time is it where you are? And more intriguingly, how much does the exact moment matter in the grand scheme of things? Time, like speed, often feels like an unshakable constant. But as we explore the possibility of tachyons and what they represent, we might begin to see time itself in a new light. Now, if you find these explorations intriguing, I encourage you to like this video and perhaps subscribe. It helps this little corner of the internet find others who are equally curious about the deep mysteries of the universe. But let's not linger too long on the formalities. We're here to explore something far more exciting. So let's dive in and start our journey into the world of tachyons and their potential to shatter the boundaries of speed. We all know about the speed of light. It's a fundamental constant in our understanding of the universe, one that even dictates the very nature of how time and space behave. But how did we arrive at this notion that nothing can go faster than light? The idea is rooted in Einstein's theory of relativity, which revolutionized how we perceive time and space. According to relativity, as objects approach the speed of light, their mass increases, and it requires more and more energy to accelerate them further. At the speed of light, this energy requirement becomes infinite, which is why we say that nothing can exceed this limit. But what if there was an exception to this rule? What if there existed particles that, by their very nature, could travel faster than light without violating the laws of physics? That's where tachyons come into play. These theoretical particles are not just faster than light, but are thought to exist at all times as a way of breaking the rules that govern the universe's speed limit. The mere concept of tachyons challenges everything we think we know about the nature of reality, space, and time. Before we continue, take a moment to think about the implications. If tachyons exist, they could provide a way to communicate faster than light, a way to break the barrier of time itself. If we could harness them, the possibilities would be endless. But before we get ahead of ourselves, let's take a step back and examine how tachyons were first proposed and what they might mean for the future of science. The idea of tachyons was introduced in the 1960s by physicist Gerald Feinberg. He was working with the equations that govern the behavior of particles in relativistic physics, and when he applied these equations to hypothetical particles that always travel faster than light, he found that these particles didn't violate any of the known laws of physics. In fact, they seemed to fit quite neatly into the framework of quantum mechanics. He named these particles tachyons, deriving the name from the Greek word for swift, tachys. And thus the idea of particles that could travel faster than light was born. But the concept of tachyons raises many questions. For one, if tachyons were real, how would we observe them? How could we detect something that is beyond the speed of light? And more importantly, what does it mean for our understanding of time, space, and causality? To understand the significance of tachyons, we must first consider the fabric of spacetime itself. Spacetime, as Einstein taught us, is a four-dimensional continuum that combines the three dimensions of space with the dimension of time. This fabric of the universe bends and warps around objects with mass, creating what we perceive as gravity. The faster you move through space, the more time slows down for you, a phenomenon known as time dilation. But if tachyons could exceed the speed of light, what effect would that have on time? Could they somehow travel backward in time, breaking the chain of cause and effect? It's an idea that seems almost too strange to contemplate, but that's exactly what makes tachyons so fascinating. Their very existence would challenge everything we understand about the relationship between time and space. Imagine being able to send a message into the past, or to observe events as they unfold faster than the speed of light. The implications are mind-boggling. And yet, despite their theoretical nature, tachyons remain a subject of serious scientific inquiry. But how would we test for tachyons? How could we detect a particle that exists outside of our normal understanding of speed and time? In a sense, finding tachyons is akin to trying to detect a shadow in a pitch-black room. If they exist, they don't interact with the universe in the same way that normal particles do. They don't leave a trail we can easily follow. But physicists have devised ways to indirectly detect their effects. One such method is through their potential role in quantum field theory, where they might influence the behavior of certain fields and particles. Still, the search for tachyons remains elusive. In addition to their theoretical implications, tachyons could have profound effects on the way we understand the universe. For example, if they can travel faster than light, they might also be able to move through time, leading to the possibility of time travel. In fact, the so-called tachyonic anti-telephone is a thought experiment that explores the idea of sending messages faster than light, potentially allowing communication between different points in time. While it's purely theoretical, it's an example of how tachyons could potentially open up new possibilities for how we interact with the universe. But we must be cautious. The idea of tachyons, while exciting, is not without its challenges. For one, they seem to defy the basic principles of causality, the idea that cause always precedes effect. If tachyons can travel backward in time, they could potentially create paradoxes, where the effect occurs before the cause. These types of paradoxes are a central concern for physicists studying tachyons and the possibility of time travel. But even if tachyons do not allow for time travel, their ability to move faster than light could still revolutionize our understanding of physics. And so, as we venture into this topic, we'll explore the implications of tachyons on our understanding of time, space, and the very nature of the universe. We'll examine the theoretical underpinnings of these particles, their potential to change the way we think about the speed of light, and the challenges that come with trying to study something that may not even exist in the way we understand reality. But more than anything, we'll ask the fundamental question: what would it mean for the universe if tachyons are real? What would it mean for our place in it? So now that we've introduced the concept of tachyons, let's begin to unravel their mystery. How do they challenge the very fabric of space-time? And what does their existence, or lack thereof, say about the limits of our universe? In the world of physics, few concepts are as universally accepted and as deeply ingrained in our understanding of reality as the speed of light. We measure distances in light years, define time by the ticking of clocks that are set by the very motion of light, and rely on the constant speed of light to understand everything from the vastness of the cosmos to the smallest particles. But why has the speed of light become such a fundamental constant in the laws of nature? And what does it tell us about the structure of the universe? At its core, the speed of light represents a limit. Not just any limit, but one that seems to govern everything in the universe, from the passage of time to the movement of galaxies. The idea that nothing can exceed the speed of light, approximately 299,792 kilometers per second in a vacuum, is one of the pillars of modern physics. It's a concept that we take for granted in our everyday lives, yet it holds profound implications for the way we understand the universe. The The journey to understanding the speed of light began long before Einstein came along. For centuries, scientists wondered whether light was a physical entity that travelled through space, and if so, at what speed. In the 17th century, the Danish astronomer Ole Rømer was the first to make a significant breakthrough by observing the motion of Jupiter's moons. He noticed that the timing of their orbits seemed to change depending on whether Earth was moving towards or away from Jupiter. From this, he inferred that light had a finite speed, meaning it took time to travel from one point to another. This was the first hint that light might not be instantaneous. It wasn't until the 19th century, however, that scientists began to measure the speed of a light with greater precision. Albert Michelson, an American physicist, is credited with determining the speed of light with remarkable accuracy in the late 1800s. Using a rotating mirror and a series of carefully timed measurements, Michelson found that light travels at approximately 299,792 kilometers per second. This measurement would go on to become one of the most precise and important constants in all of physics. But it was Albert Einstein's theory of special relativity in the early 20th century that transformed our understanding of the speed of light. Einstein proposed that the speed of light is not only a constant, but also a fundamental limit in the universe. According to his theory, nothing can travel faster than the speed of light in a vacuum. This was a radical departure from the classical Newtonian view of the universe, where space and time were considered absolute and unchanging. Einstein's breakthrough came when he realized that the laws of physics are the same for all observers, regardless of their relative motion. This led to the idea that space and time are not separate, rigid entities, but are instead intertwined into a single, flexible fabric known as spacetime. The speed of light in this framework became the ultimate speed limit, a constant that governs the relationship between time and space. Nothing can move faster than light without breaking the very structure of the universe itself. To understand the significance of this speed limit, we need to dive into the relationship between time and space. In the world of special relativity, the speed of light is not just a measure of how fast something moves through space. It is also intimately tied to the flow of time. As an object approaches the speed of light, time itself slows down for that object. This phenomenon, known as time dilation, means that for an observer moving at near-light speeds, time would appear to pass more slowly compared to someone at rest. This effect has been experimentally confirmed in a variety of ways, including with particles travelling at high speeds and even with precise atomic clocks flown on airplanes. Time dilation is just one of the many strange consequences of the speed limit imposed by the speed of light. Another consequence is length contraction. As an object moves closer to the speed of light, its length in the direction of motion appears to shorten from the perspective of a stationary observer. These effects are not just theoretical. They have been observed in experiments with particles moving at relativistic speeds, and they play a crucial role in technologies like GPS, where the satellites in orbit experience different gravitational and velocity effects compared to clocks on Earth. One of the most profound implications of the speed of light as a limit is its connection to causality. Causality is the principle that cause precedes effect, that events in the universe unfold in a specific order. If something could travel faster than light, it could potentially violate this principle, allowing for situations where the effect happens before the cause. This could lead to paradoxes, such as the classic grandfather paradox, where a time traveller goes back in time and prevents their grandfather from meeting their grandmother, thus preventing their own birth. If tachyons, particles that could potentially exceed the speed of light, exist, they might present a challenge to this fundamental idea of causality. While we're still far from fully understanding the consequences of breaking the speed limit of the universe, the fact remains that the speed of light is a cornerstone of our physical theories. It's a limit that defines how we perceive time, space, and the very nature of reality. The speed of light is not just a measurement, it's a boundary that governs the interactions of particles, the flow of time, and even the structure of the universe itself. Yet, despite its significance, we continue to explore the possibility of what happens when we challenge this limit. Tachyons, as we will see, are one example of how theoretical physicists have explored the idea of particles that can exceed the speed of light. These particles are not just a curiosity, they represent a direct challenge to our current understanding of the universe. If tachyons exist, they would force us to reconsider everything from the nature of time itself to the fundamental laws that govern how particles move and interact. But before we dive deeper into the concept of tachyons, it's important to reflect on just how deeply embedded the speed of light is in our view of the universe. It is the one constant that ties together so many aspects of the physical world, from the speed at which information travels to the way we define time itself. Understanding the speed of light and its role in shaping the universe is essential to understanding not only the past and present of the cosmos, but also its potential future. As we move forward, we will explore how tachyons, as theoretical particles, might break the speed barrier and what that could mean for our understanding of physics. But first, we must ask, if the speed of light is the ultimate speed limit, what happens if we find something that surpasses it? Could we enter a new realm of physics, where time and space behave differently than we've ever imagined? This is the question at the heart of the tachyon theory, and it's one that will guide us as we continue our journey through the mysteries of the universe. As we venture deeper into the heart of theoretical physics, we come to a concept that might feel almost like science fiction: tachyons. These are particles that, according to the mathematical framework of modern physics, are proposed to move faster than light. On the surface, this idea sounds absurd. After all, we've already established that the speed of light is the ultimate speed limit of the universe, right? So how can anything exceed that limit without breaking the very rules that govern the physical world? The answer, at least for now, is that tachyons may not break those rules. They may simply operate in a different way than anything we've encountered before. Tachyons were first introduced in the 1960s by the physicist Gerald Feinberg. He was exploring a particular mathematical feature of special relativity and noticed that if a particle were to travel faster than the speed of light, it could still fit within the framework of physics, at least theoretically. Feinberg didn't just speculate on the possibility of these particles existing. He also suggested that these faster-than-light particles could have profound implications for the nature of reality itself. If tachyons exist, they would not only challenge our understanding of speed, but also force us to reconsider what we think we know about time, space, and causality. The key to understanding tachyons lies in their nature. Unlike ordinary particles, which have real mass and move through spacetime at speeds less than the speed of light, tachyons are theorized to have what is known as imaginary mass. This term doesn't mean that tachyons are imaginary in the sense that they don't exist. It's a mathematical term, a result of the equations governing relativistic physics. Imaginary mass means that tachyons would not behave in the same way as ordinary matter. They would, in theory, always travel faster than light, and would have an energy that increases as their speed increases. To appreciate what this means, let's step back and consider the relationship between energy, mass, and speed. In classical physics, we learn that an object's energy increases as it moves faster, and that it requires more and more energy to approach the speed of light. But for tachyons, the opposite would be true. The faster a tachyon moves, the more energy it would have. This is where the strange and impossible part comes in. Tachyons would have infinite energy at the speed of light, but unlike particles with real mass, they would not be constrained by the usual limitations of acceleration and energy. The existence of tachyons would suggest that the fabric of spacetime itself might be more flexible than we thought. Special relativity, the theory that governs our understanding of space and time, relies on the idea that the speed of light is the ultimate upper limit. According to Einstein, the faster something moves, the more time it dilates, and the greater the energy required to continue accelerating. But tachyons, moving faster than light, wouldn't experience time in the same way. In fact, they might not even experience time at all in the traditional sense. This leads to a very interesting question. What would it mean for something to move faster than light? In the realm of relativity, time is intertwined with space to form what is known as spacetime. When objects travel through spacetime at speeds less than the speed of light, they experience time in a way that is relative to their motion. But if tachyons can exceed the speed of light, they might be able to experience time in reverse, moving backward in time, so to speak. This idea opens the door to time travel, a concept that has fascinated scientists and storytellers alike. At first glance, time travel through tachyons might seem like an exciting prospect. Imagine being able to send messages into the past, or to witness events that happened long before you were born. In theory, tachyons could allow for faster-than-light communication, even between different points in time. This is the foundation of the so-called tachyonic antitelephone, a thought experiment that imagines using tachyons to send signals back in time. While this idea might sound outlandish, it's an example of how tachyons challenge our understanding of time and space. However, the possibility of tachyons moving backward in time also presents serious challenges. If tachyons could travel through time, they might create paradoxes, such as the grandfather paradox, where an action taken in the past prevents the very event that led to it. If you could send a signal back in time to change something that happened, would that change the future in ways that are impossible to predict? Would it break the laws of causality, the principle that cause always precedes effect? This is a central concern for physicists studying tachyons, as the existence of particles that can move faster than light could open up a whole new set of questions about the fundamental nature of time. In addition to the implications for time travel, tachyons might also offer new insights into the behavior of quantum fields. Quantum field theory, which underpins much of modern physics, posits that the universe is filled with fields that interact with particles. These fields are the fundamental building blocks of matter and energy, and understanding how they work has led to significant breakthroughs in our understanding of particle physics. Tachyons, if they exist, could interact with these fields in ways that we don't yet fully understand. The discovery of tachyons might open up new avenues of research into the very nature of quantum fields and the forces that govern them. However, the challenge remains that tachyons, as fascinating as they may be, are purely theoretical at this point. No experimental evidence has yet been found to support their existence, and the theoretical work that suggests their possibility is still the subject of ongoing debate among physicists. Some believe that tachyons may never be found because they do not interact with ordinary matter in the same way as other particles, making them nearly impossible to detect. Others speculate that we might one day find indirect evidence of tachyons, perhaps through their effects on other particles or fields. But for now, tachyons remain a tantalizing possibility, a glimpse into a world of physics that could upend everything we know about the universe. Theoretical physicists have long speculated about the possibility of particles that could break the speed limit of the universe. Tachyons are not the only candidates. In fact, the concept of faster-than-light travel is woven into the fabric of many speculative theories about the universe. From wormholes to exotic matter, physicists have proposed a range of ideas that challenge the constraints of space and time. Tachyons, however, remain one of the most intriguing and mysterious possibilities. What makes tachyons especially compelling is that they are not just a theoretical curiosity. They are a potential link between the known and the unknown. They represent a bridge between the well-established laws of physics and the uncharted territory of what lies beyond our current understanding. If tachyons exist, they would represent a fundamental breakthrough in our understanding of the universe, one that could change everything from the way we think about time to the very structure of reality itself. As we continue to explore the concept of tachyons, we must consider the profound implications of their existence. If they can travel faster than light, what other mysteries of the universe could they unlock? Could they provide a path to understanding the deeper laws of the cosmos, from quantum mechanics to the nature of space-time? And what might it mean for us, as human beings, to confront the possibility of a universe where the speed of light is no longer the ultimate limit. For now, tachyons remain a glimpse into the impossible, a theoretical window into a world where the laws of physics are not as fixed as we once thought. But as we continue to push the boundaries of our knowledge, who knows what new discoveries await? Perhaps, one day, we will uncover the true nature of these elusive particles and in doing so, take a giant step toward understanding the very fabric of the universe. The concept of the speed of light as a fundamental limit is so deeply embedded in our understanding of the universe that it's easy to forget just how revolutionary this idea really is. For centuries, humanity believed that the universe was governed by a different set of rules, where space and time were more malleable and open to interpretation. But when Albert Einstein introduced his theory of special relativity in 1905, everything changed. It wasn't just the world of physics that was turned upside down, but our entire perception of the cosmos. The speed of light became something more than a number on a measurement scale. It became a cornerstone of modern science, a boundary that dictates how we understand everything from the motion of particles to the structure of space itself. Why does the speed of light matter so much? It's not simply about how fast something can move, it's about how the entire fabric of the universe is woven together. The speed of light defines the way we experience time, space, and causality. If you were to exceed this speed, the entire structure of reality as we know it would begin to unravel. To understand why, we need to look closely at what the speed of light really represents and how it shapes the laws that govern the universe. The speed of light is not just a limit for objects travelling through space. It also sets the pace for how information travels across the universe. In Einstein's theory of relativity, the speed of light is the ultimate speed limit because it is the fastest speed at which information or any kind of signal can propagate. When you send a signal from one point in space to another, no matter how powerful that signal is, it can never travel faster than the speed of light. This means that if we look far out into the universe, the light we see from distant stars and galaxies has travelled across vast distances, taking millions or even billions of years to reach us. When we look at the night sky, we're essentially looking back in time. This brings us to the concept of causality, the idea that causes must precede effects. Causality is one of the fundamental principles that underpins our understanding of the universe. It dictates that events unfold in a specific sequence. Something happens first, and then something else happens as a result. But if we could travel faster than light, we would enter a realm where this principle starts to break down. If information or matter could travel faster than the speed of light, the relationship between cause and effect could be reversed. A signal could reach its destination before it was even sent, creating situations where the effect occurs before the cause. This is where the real danger of breaking the light barrier becomes apparent. If tachyons, or any other faster-than-light particles exist, they would challenge this fundamental understanding of how the universe operates. But why is the speed of light tied so closely to causality and the structure of spacetime? The answer lies in the way spacetime itself behaves. In Einstein's relativity, space and time are not separate entities but are intertwined into a single, four-dimensional continuum. This fabric of spacetime bends and warps in response to mass and energy, creating the phenomenon we perceive as gravity. As objects move through space, they also move through time. But the relationship between space and time is not fixed. It is flexible and dependent on the speed at which something is moving. This flexibility is what allows the speed of light to play such a central role in the structure of the universe. The faster an object moves, the more its experience of time changes. For an observer moving at a high speed, time appears to slow down compared to someone who is at rest. This effect, known as time dilation, becomes more pronounced as the object's speed approaches the speed of light. But no matter how fast you go, you can never reach the speed of light, because doing so would require an infinite amount of energy. This is the essential point that makes the speed of light a hard limit. If you were somehow able to surpass this limit, you would have to discard all the laws that govern spacetime, and the consequences would be catastrophic. The speed of light is more than just a limit. It's the cornerstone of the entire structure of spacetime. It defines how distances are measured, how time is experienced, and how causality is maintained. Without the speed of light as a limit, the very nature of the universe would change. Time would no longer flow in a predictable way, and the sequence of events that we take for granted could no longer be trusted. If tachyons are real, they could disrupt this delicate balance and introduce paradoxes that we can't yet comprehend. This brings us to another important aspect of the light barrier, the concept of light itself. Light, as we know, is the fastest thing in the universe. It travels at 299,792 kilometers per second in a vacuum, a speed that has been measured with incredible precision. But light is more than just a fast-moving particle. It's also the carrier of information in the universe. When we look at distant stars or galaxies, we are receiving information that has travelled across vast stretches of space for billions of years. That light carries with it the history of the universe, the birth and death of stars, the collision of galaxies, the very evolution of the cosmos itself. If we could exceed the speed of light, we would no longer be bound by the limits of space and time. We could, in theory, send information across vast distances in an instant, but this too would create problems. If we could send information faster than light, we could potentially send a message back in time, altering the course of history in ways that would be impossible to predict. This is where the idea of tachyons and their connection to time travel comes into play. If tachyons can exceed the speed of light, they could open the door to a new way of interacting with the universe, one where time is no longer a rigid, forward-moving force but something more fluid and unpredictable. So, why does the light barrier matter? It's not just about the speed at which things move, it's about the very nature of reality itself. The speed of light is the key that unlocks our understanding of time, space, and causality. It's a limit that defines the structure of the universe and governs the interactions between particles, forces, and fields. Without the speed of light as a boundary, the universe would become a very different place, one where the laws of physics as we know them would no longer apply. If tachyons, or any other faster-than-light particles exist, they would challenge everything we know about the cosmos and force us to rethink the very foundations of physics. But as we look at the possibility of tachyons and other faster-than-light phenomena, we must ask ourselves, what would it mean for us as human beings? Would the discovery of such particles allow us to break free of the constraints of time and space? Could we travel to distant stars or even journey backward in time? These are questions that continue to intrigue and inspire physicists, and they lie at the heart of the mystery of tachyons. As we explore this topic further, we'll consider the implications of tachyons and what they might mean for the future of science. But for now, it's clear that the speed of light is not just a speed, it's a fundamental boundary that shapes the entire structure of the universe. Tachyons are, in many ways, one of the most mysterious and perplexing concepts in modern physics. These hypothetical particles are not merely an abstraction or an imaginary construct. They represent a serious challenge to our current understanding of space, time, and the fundamental laws of nature. The very name tachyon comes from the Greek word tachys, meaning swift or quick, and indeed, the key feature of these particles is their ability to travel faster than light. But before we delve into the theoretical implications of such particles, it's important to understand what tachyons actually are, what properties they would have, and how they fit into the broader framework of physics. To start, tachyons are particles that, in the context of special relativity, are postulated to have an imaginary mass. This might sound a bit odd, as the concept of mass is usually associated with real, measurable quantities. But in the realm of theoretical physics, the term imaginary has a very specific mathematical meaning. In the equations of special relativity, mass appears in a way that allows for certain particles to have what is known as imaginary mass. This concept does not imply that tachyons don't exist or are purely fantastical. Rather, it means that their mass, when plugged into the equations of relativistic physics, doesn't follow the typical rules for ordinary particles. Instead, tachyons are described in such a way that they are inherently tied to faster-than-light travel. The concept of imaginary mass might be difficult to wrap your mind around initially, but it's a crucial piece of the puzzle. In special relativity, particles with real mass cannot exceed the speed of light because, as they approach that speed, their mass increases, and the energy required to continue accelerating them grows infinitely. This is the famous relativistic mass increase that leads to the impossibility of reaching or surpassing the speed of light. However, tachyons are different. Due to their imaginary mass, they don't face this issue. Instead, they are theorized to exist at speeds greater than the speed of light from the moment they are created. The faster they move, the more energy they have, in direct contrast to the behavior of ordinary particles, which require increasingly more energy to approach the speed of light. But what does this all mean in practical terms? Well, the theoretical existence of tachyons opens up a host of fascinating possibilities. For one, tachyons would be able to move through spacetime in ways that ordinary particles cannot. If tachyons exist, they would have properties that challenge everything we know about the way the universe works, particularly when it comes to our understanding of time and causality. The relationship between tachyons and time is one of the most intriguing aspects of their theoretical nature. In Einstein's theory of special relativity, time is intimately connected with the speed at which an object moves. As an object approaches the speed of light, time for that object appears to slow down relative to a stationary observer. But what happens when a particle exceeds the speed of light? The theory suggests that tachyons could, in some sense, experience time in reverse. If tachyons move faster than light, they could potentially travel backward in time, opening up the possibility of time loops and paradoxes. This leads to some of the more mind-bending implications of tachyons, as they may not only challenge our understanding of speed, but could also alter the very fabric of time itself. In addition to their speed and time-related properties, tachyons would also interact with the quantum fields that make up the universe. Quantum field theory is one of the cornerstones of modern physics, describing how particles interact with each other and with the fields that permeate space. In this context, tachyons could play a significant role in the behavior of these fields. In fact, some theories suggest that tachyons could have important implications for the creation and dynamics of the universe itself. If tachyons were present in the early moments of the universe, they could have influenced the way matter and energy were distributed, shaping the cosmos in ways that we are still trying to understand. One of the most fascinating ideas related to tachyons is the concept of vacuum polarization. This refers to the way that the quantum vacuum, or the lowest possible energy state of space, can be altered by the presence of particles and fields. If tachyons were to interact with this vacuum, they could potentially create fluctuations in the vacuum itself, altering the way that other particles behave. These fluctuations could have far-reaching consequences for everything from particle physics to cosmology, affecting how forces like gravity and electromagnetism manifest across the universe. Despite their theoretical nature, tachyons are not purely a mathematical curiosity. In fact, their existence is supported by a number of well-established principles in physics. For example, tachyons are consistent with the mathematical structure of quantum field theory and the equations of special relativity. They don't violate any of the fundamental laws of physics. Instead, they suggest that our current understanding of space, time, and the speed limit of the universe may be incomplete. If tachyons were to be discovered, it would represent a monumental shift in our understanding of the laws that govern the cosmos. However, the existence of tachyons also presents significant challenges. The most obvious challenge is that they are, as of now, purely hypothetical. There is no direct experimental evidence to support their existence, and detecting them would be an incredibly difficult task. One of the reasons for this is that tachyons are thought to interact with ordinary matter in very subtle ways. Unlike other particles, which can be detected by their interactions with the electromagnetic field, tachyons are expected to be nearly undetectable by conventional means. They would not emit light or interact strongly with matter, making it hard to observe them directly. Despite these challenges, physicists continue to explore the theoretical implications of tachyons. Some have proposed that we might detect their presence indirectly, by looking for the effects they might have on other particles or fields. For example, tachyons could potentially influence the behavior of quantum fields, leading to subtle changes in the way that particles interact with each other. These changes could provide the first clues that tachyons exist, even if we can't observe them directly. Another avenue of research involves the potential use of tachyons in practical applications. If tachyons can indeed move faster than light, they might open up the possibility of faster-than-light communication or even time travel. While these ideas are purely speculative at this point, they represent a tantalizing glimpse into a future where the laws of physics as we know them could be radically altered. Imagine being able to send a message to the past or to communicate with distant parts of the universe instantaneously. The implications for technology, society, and our understanding of the universe would be staggering. But even if tachyons are never discovered or proven to exist, their theoretical nature has already had a profound impact on our understanding of physics. The idea of tachyons forces us to confront the limits of our current knowledge and to explore the possibility that the universe may be far more complex than we can imagine. It challenges us to rethink the fundamental laws of nature and to ask questions about the nature of space, time, and reality itself. In the end, tachyons are more than just theoretical particles. They represent a doorway to a new understanding of the universe. Whether they are ever discovered or not, they have already opened up new possibilities in the realm of physics, pushing the boundaries of what we know about the cosmos and our place within it. To understand tachyons and their potential to shatter the speed barrier, we must first dive into the theoretical foundations that give rise to them. These particles may seem like a far-fetched idea at first, but they arise from well-established principles in physics, particularly the theories that govern the behavior of particles in high-energy environments. The more we explore the theoretical underpinnings of tachyons, the clearer it becomes that they aren't just a product of imagination, they're an outgrowth of the deeper structures of relativity and quantum mechanics. The theoretical foundations of tachyons are rooted in the work of special relativity, a theory formulated by Albert Einstein in the early 20th century. Special relativity revolutionized the way we think about space and time, showing that they are not separate, independent entities, but are instead part of a unified four-dimensional continuum known as spacetime. According to special relativity, the speed of light is the ultimate limit for any particle with mass. As objects approach the speed of light, their mass increases and the energy required to continue accelerating them grows exponentially, making it impossible for them to reach or exceed this limit. However, the equations that describe relativistic motion leave open the possibility for particles that behave in ways that are radically different from those we encounter in everyday life. This is where tachyons come in. In the framework of special relativity, particles that move faster than light are theoretically allowed, provided they have imaginary mass. This is a key point that sets tachyons apart from regular particles. To understand what it means for a particle to have imaginary mass, we need to look more closely at the mathematics of special relativity. In the relativistic equations that describe particle motion, mass is a key factor in determining how a particle behaves. For particles that travel slower than light, the mass is a real number, meaning it's positive and measurable. As the particle approaches the speed of light, its relativistic mass increases, and at the speed of light, its mass would theoretically become infinite. This is why no particle with real mass can reach or exceed the speed of light. It would require an infinite amount of energy to do so. But for particles with imaginary mass, the situation is different. Imaginary mass arises when we take the equations of relativity and solve for the mass of a particle that moves faster than light. In this context, imaginary is a mathematical term, and it refers to a quantity that can't be measured in the same way as real mass. When a particle's mass is imaginary, the equations governing its motion behave differently than they do for particles with real mass. These particles don't experience the same restrictions when it comes to their speed, allowing them to exceed the speed of light without violating the laws of physics. Now, this may sound highly theoretical and abstract, but the concept of imaginary mass is not entirely new. In fact, the idea of imaginary mass has appeared in various contexts within physics, particularly in the study of fields and particles in quantum mechanics. The notion that particles can have different kinds of mass, including imaginary mass, is consistent with the mathematical structures of quantum field theory, a theory that describes the interactions of subatomic particles and the fields that permeate space. Quantum field theory is the foundation of much of modern physics, and it describes the universe as being filled with fields, electromagnetic fields, gravitational fields, and more that interact with the particles that make up matter. The behavior of these fields is governed by the principles of quantum mechanics, which dictate how particles can interact, exchange energy, and move through space. The equations that describe quantum fields often include terms that can have imaginary values, allowing for unusual and counterintuitive phenomena. In this context, tachyons are simply another type of particle that arises naturally from the mathematical framework of quantum field theory. The concept of tachyons also finds a place in the broader framework of quantum mechanics. In quantum theory, particles do not have definite positions or velocities in the same way that classical particles do. Instead, they exist in a state of uncertainty, described by a wave function that represents the probability of finding the particle in a particular place or with a particular velocity. This uncertainty is a fundamental feature of quantum mechanics, and it leads to the idea that particles can have a range of possible speeds, including those that exceed the speed of light. In fact, some versions of quantum field theory suggest that tachyons may be present in the vacuum of space itself. According to these theories, the vacuum is not empty, but is instead filled with fluctuating fields that give rise to virtual particles. These virtual particles constantly pop in and out of existence, and their interactions are responsible for many of the phenomena we observe in the quantum world. Tachyons, in this context, could be part of the vacuum fluctuations, momentarily appearing and disappearing in ways that we cannot directly observe, but which could have significant effects on the properties of quantum fields. The theoretical foundation for tachyons also ties into the broader field of relativistic quantum mechanics. Relativistic quantum mechanics seeks to combine the principles of quantum mechanics with the theory of special relativity, creating a framework that can describe the behavior of particles moving at relativistic speeds. In this context, tachyons appear as a natural extension of the equations that describe relativistic particles. They represent a type of solution to the relativistic wave equation that predicts the existence of particles that always move faster than light. One of the key results of relativistic quantum mechanics is the prediction that particles can exhibit both particle-like and wave-like behavior. This wave-particle duality is a hallmark of quantum mechanics and has been confirmed in countless experiments. The presence of tachyons in this framework suggests that faster-than-light particles could also exhibit both wave-like and particle-like properties, behaving in ways that are fundamentally different from anything we encounter in our everyday experience. The idea that tachyons might exist in a quantum field leads to some intriguing possibilities. If tachyons can interact with the quantum fields that permeate space, they could play a role in shaping the behavior of particles and forces at the most fundamental level. Some theorists have speculated that tachyons might be involved in the creation of new particles, or that they could influence the behavior of other particles in ways that we don't yet fully understand. Their presence in the vacuum could have profound implications for the way we understand the structure of the universe, particularly when it comes to the origin of matter and the forces that govern the cosmos. In the context of string theory, another framework of theoretical physics, tachyons play an important role. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings can exist in multiple dimensions, and their vibrations determine the properties of the particles they give rise to. In certain versions of string theory, tachyons appear as a natural feature of the theory, signalling instability in the vacuum state of the system. These tachyonic instabilities are thought to be related to the process of spontaneous symmetry breaking, a phenomenon that helps explain the differences between the fundamental forces of nature. Despite the theoretical elegance of tachyons and their connection to well-established principles in physics, they remain elusive. The fact that tachyons are predicted to have imaginary mass means that they are not directly detectable by current experimental techniques. Unlike regular particles, which interact with electromagnetic fields and can be observed through their interactions with matter, tachyons are thought to have a much weaker interaction with ordinary particles. This makes detecting them through traditional means incredibly challenging. However, their theoretical significance is undeniable. Tachyons push the boundaries of our understanding, forcing us to confront the limits of our current knowledge. If they exist, tachyons could revolutionize our understanding of the universe, challenging everything from the speed of light to the very nature of time itself. Even though they remain purely hypothetical for now, the theoretical framework behind tachyons offers a glimpse into the possibilities that await as we continue to explore the frontiers of physics. To truly grasp the significance of tachyons and their role in challenging the speed limit of the universe, it's essential to understand the deeper nature of time and space. These two concepts are often treated as separate entities in our everyday experience, but in the realm of physics, they are inextricably linked together. Time and space form a unified framework known as spacetime, a fundamental feature of the universe that Einstein's theory of relativity revealed to us. This interconnected fabric of time and space is not just a mathematical concept, but a real aspect of the cosmos that shapes everything from the behavior of light to the motion of planets. The idea that time and space are interconnected was not always obvious. In classical physics, time was treated as an independent, constant backdrop against which events unfold. Similarly, space was seen as a vast, empty arena in which objects moved. But this view of the universe began to change in the early 20th century, when Einstein introduced his theory of special relativity. According to special relativity, time and space are not fixed and separate. They are relative and depend on the observer's motion. The notion that time and space are connected was revolutionary, and has since become one of the cornerstones of modern physics. At the heart of this concept is the idea that the speed of light is constant for all observers, regardless of their motion. This means that no matter how fast you're moving, light will always travel at the same speed. But this also means that the way we experience time and space depends on how fast we're moving relative to other objects. If you were to travel at a significant fraction of the speed of light, time would slow down for you relative to someone at rest. This phenomenon, known as time dilation, is a direct consequence of the way space and time are woven together into space-time. One of the most striking implications of this is that time is not an absolute constant. Rather, it is something that is experienced differently depending on your motion through space. If two observers are moving relative to each other, they will measure different amounts of time for the same event. To one observer, a second may seem to pass normally, but to the other, it could appear to stretch or compress depending on their relative velocity. This may sound strange, but it has been confirmed in countless experiments, from the behavior of particles moving at high speeds to the operation of GPS satellites orbiting Earth. The fabric of space-time also affects the way objects move through space. According to general relativity, space and time are not merely passive stages upon which events occur. They are dynamic and can bend and warp in response to the presence of mass and energy. This warping of space-time is what we perceive as gravity. When a massive object, such as a planet or a star, is placed in space-time, it creates a curvature that affects the motion of nearby objects. Rather than thinking of gravity as a force that pulls objects together, as was the traditional view in Newtonian physics, General relativity tells us that gravity is the result of objects following the curved paths created by the warping of spacetime itself. This understanding of gravity leads to a completely new way of thinking about the universe. Space and time are not independent entities. They are part of a single, four-dimensional continuum that can bend and stretch. The faster an object moves through space, the more its experience of time changes. The more massive an object is, the more it warps the fabric of space-time around it. Everything is interconnected, from the motion of galaxies to the passage of time on Earth. It's within this framework of space-time that tachyons would exist. If these hypothetical particles could exceed the speed of light, they would be moving through space-time in ways that ordinary particles cannot. As we have already seen, tachyons are proposed to have imaginary mass, which means they do not experience space-time in the same way as objects with real mass. They would not be constrained by the same limits that apply to ordinary particles. This raises the question, if tachyons can travel faster than light, how would they interact with the fabric of space-time? The possibility of tachyons challenges our understanding of space-time itself. In Einstein's theory, space-time is a unified, interconnected entity that is shaped by the motion of objects and the presence of mass. If tachyons exist, they could move in ways that defy the usual rules of space-time, potentially even allowing them to travel backward in time. This would create a situation where cause and effect could be reversed, leading to paradoxes and inconsistencies in the flow of time. Such effects are difficult to reconcile with our current understanding of physics, and they suggest that if tachyons do exist, they may require us to fundamentally rethink our conception of space-time. To further appreciate the implications of tachyons on space-time, we need to consider the nature of time itself. Time, in the classical sense, was often thought of as a linear, irreversible progression. It moves forward, from the past to the present to the future. But relativity teaches us that time is more than just a sequence of events. It is a dimension that is deeply connected to the space in which we live. Just as we can move through space in three directions, up/down, left/right, forward/backward, we also move through time, and the passage of time is relative to our motion through space. For particles moving at or near the speed of light, time slows down relative to an observer at rest. This is time dilation in its simplest form. The faster an object moves, the slower time passes for it relative to someone who is not moving. This effect becomes more pronounced as the object approaches the speed of light. But what happens when a particle exceeds the speed of light, as tachyons are proposed to do? According to the equations of special relativity, particles with imaginary mass should experience time in reverse. If tachyons can move faster than light, they would effectively be moving backward through time, leading to the possibility of time travel. This idea of backward time travel is one of the most fascinating and puzzling aspects of tachyons. If particles can move faster than light, they might be able to violate the principle of causality, the idea that causes must precede effects. If tachyons are able to travel backward in time, they could create situations where the effect occurs before the cause, leading to paradoxes that challenge our basic understanding of how events unfold in the universe. This is a subject of intense debate among physicists, as it suggests that our current models of spacetime may not be complete, and new theories may be needed to account for these strange and unexpected phenomena. At the same time, the idea of tachyons and their relationship with spacetime also opens up exciting possibilities. If tachyons can move faster than light and travel through time, they could provide a way to communicate across vast distances in an instant. In theory, tachyons could also be used for time travel, allowing us to send information or even matter backward in time. This would fundamentally change the way we think about the flow of time, the nature of causality, and the possibilities of human exploration. But for all these possibilities, we are still left with the central question: are tachyons real, or are they just a mathematical curiosity? While the theoretical framework of spacetime suggests that tachyons could exist, there is currently no direct experimental evidence to support their existence. The idea of tachyons remains a speculative one, and scientists continue to search for clues that might indicate their presence. Whether or not tachyons exist, however, the study of these particles forces us to reconsider the very nature of time and space, and it challenges us to think beyond the limits of our current understanding. As we continue to explore the mysteries of spacetime and tachyons, it's clear that the interconnected fabric of time and space is far more complex than we once thought. The possibility of faster-than-light particles challenges our assumptions about the universe, and it may ultimately lead to a deeper understanding of the fundamental nature of reality. Whether or not tachyons are real, their theoretical existence invites us to rethink the very fabric of spacetime and the limits of what is possible in the universe. In the realm of physics, the idea that breaking the speed limit might break time itself is one of the most intriguing and paradoxical concepts that comes up when discussing tachyons. At the heart of this question lies a fundamental principle of modern physics. Time and space are deeply intertwined. Time is not a rigid, unchanging backdrop against which events happen. Instead, it is part of the fabric of space-time, a four-dimensional continuum that bends and warps depending on the mass, energy, and motion of objects. If tachyons exist and can travel faster than light, they would not just be defying the speed limit, they could be altering the very structure of time itself. Before we dive deeper into this fascinating question, it's important to revisit one of the core ideas of Einstein's special relativity: the relationship between time and speed. According to special relativity, time is relative, meaning it is experienced differently by observers moving at different speeds. As an object approaches the speed of light, time slows down for that object relative to someone at rest. This effect, known as time dilation, has been confirmed through numerous experiments. For instance, atomic clocks flown on airplanes or placed on satellites tick slightly more slowly than identical clocks on the ground due to their higher speeds and the gravitational effects they experience, but this slowing of time is only part of the story. The real question comes when we ask what happens if an object moves faster than light. In the framework of special relativity, this scenario presents some profound challenges. The equations of special relativity work seamlessly for objects moving at subluminal speeds, slower than light. But when you extend those equations to objects that exceed the speed of light, strange things start to happen. In particular, the relationship between time and space begins to break down. And this is where tachyons, as theoretical faster-than-light particles, enter the conversation. If tachyons exist and are capable of moving faster than light, one of the most interesting and perplexing implications is that they might not experience time in the same way as ordinary particles. According to the mathematical structure of relativity, as a particle's speed increases, its experience of time slows down. At the speed of light, time essentially comes to a halt. But if a particle can move faster than light, it might experience time in reverse. This leads to the possibility that tachyons could be moving backward through time, an idea that challenges our most basic intuitions about the nature of time itself. This idea of time moving backward when faster-than-light particles are involved is not just a speculative thought experiment. It is rooted in the mathematics of special relativity. In the equations, if you solve for particles with velocities greater than the speed of light, you encounter a term that suggests time could run in reverse. For example, if a tachyon were moving faster than light, the distance it covers in space might correspond to a negative value for time. This would imply that the tachyon is not just moving forward through space, it is also moving backward in time. In a sense, tachyons could be a kind of time traveller, moving to the past as they travel faster than the speed of light. This raises a host of fascinating questions. If tachyons can travel backward in time, could they also send signals to the past? Could information travel back in time, effectively allowing for communication between different points in history? These ideas are at the core of the concept known as the tachyonic antitelephone. This thought experiment explores the possibility of using tachyons to send messages faster than light, but with the added twist that these messages could be sent to the past, potentially altering the course of events. While this idea is purely theoretical and highly speculative, it demonstrates the profound impact that faster-than-light particles could have on our understanding of time and causality. However, there is a major issue with the concept of time travel and tachyons, the potential for paradoxes. Time travel has long been a topic of fascination and a staple of science fiction, but it also brings with it a host of logical contradictions. For example, if you could send a message or a particle back in time, could you change the past in such a way that it prevents the original event from ever happening? This is the classic grandfather paradox, in which a time traveller might go back in time and prevent their own existence. If the traveller never existed in the past, how could they have travelled back in the first place? The idea of tachyons, with their potential to break the time barrier, forces us to confront these paradoxes and ask whether they could exist in a physically consistent way. Some physicists have attempted to resolve these paradoxes by suggesting that the universe has built-in mechanisms that prevent time travellers from creating contradictions. One such idea is the many worlds interpretation of quantum mechanics. According to this interpretation, when a time traveller changes something in the past, they do not alter the original timeline. Instead, they create a new parallel timeline. In this scenario, the original timeline remains intact, and the time traveller's actions create a branching universe. This idea, while intriguing, is still highly speculative and does not offer a definitive solution to the paradoxes of time travel. Another potential resolution involves the concept of self-consistency. This idea, proposed by physicist Igor Novikov, suggests that the laws of physics might prevent any action that would lead to a paradox. In other words, the universe would somehow prevent a time traveller from making changes to the past that would cause contradictions. For example, if a time traveller tried to prevent an event from happening, their actions would always be thwarted by some other force or circumstance, ensuring that the timeline remains consistent. Even though these theoretical solutions offer interesting possibilities, they still leave us with more questions than answers. The concept of tachyons and their potential to break the speed limit of the universe brings us face to face with the most fundamental issues in physics: the nature of time, the structure of causality, and the potential for time to be more flexible than we ever imagined. But what would it mean for the universe if time could be broken or manipulated in such a way? If tachyons could travel faster than light and reverse the flow of time, it would have profound implications for our understanding of cause and effect. Events might no longer unfold in a predictable order, and the linear progression of time that governs everything from the motion of planets to the aging of human beings could be thrown into disarray. The very structure of the universe could be radically different, with the past, present, and future all existing in a state of fluidity, rather than as fixed points along an immutable timeline. While we may not yet have answers to these questions, the possibility of tachyons and the potential for faster-than-light travel invites us to explore the boundaries of our understanding of time. If tachyons exist, they could hold the key to unlocking new dimensions of reality, where time and space are more fluid and less constrained by the limits we currently impose upon them. They might offer us a glimpse into a universe that operates on principles far more complex and far-reaching than we can yet comprehend. So, does breaking the speed limit break time? The answer, for now, is unclear. Tachyons offer a tantalizing possibility, but their existence would force us to confront the most profound questions in physics. Questions about the nature of time, space, and the very fabric of reality itself. As we continue to explore the potential of tachyons, we must keep in mind that the universe may not be as rigidly defined as we once thought. Time, as we know it, may be just one facet of a far more complex and mysterious structure, one that holds secrets we have yet to uncover. In order to truly understand the potential implications of tachyons on the fabric of reality, we must dive deeper into their possible role within the framework of quantum mechanics. Quantum mechanics, which governs the behaviour of particles on the smaller scales of the universe, is no stranger to unusual phenomena. From wave-particle duality to quantum entanglement, the quantum world often behaves in ways that defy common sense. This is why the concept of tachyons, theoretical particles that are faster than light, fits into the broader picture of quantum theory, which itself is no stranger to the unexpected. To explore how tachyons might fit within quantum mechanics, we must first understand a few fundamental concepts about the quantum world. Quantum mechanics tells us that particles do not have definite positions or velocities in the classical sense. Instead, they exist in a superposition of possible states, represented by a wave function, which provides the probabilities of where and how a particle might be found. This wave function evolves over time according to the Schrödinger equation, a mathematical framework that describes how the quantum state of a system changes. In the classical sense, time and space are stable and continuous. However, in quantum mechanics, both time and space are more fluid, and particles are subject to uncertainties. The famous Heisenberg uncertainty principle asserts that there is a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time. This introduces a degree of unpredictability to the behavior of particles, which is in stark contrast to the predictable motion of objects we experience in our daily lives. Tachyons, as theoretical particles that would be able to break the speed of light, push this uncertainty to an extreme, raising the question of how they would fit into the quantum framework. The first place we might encounter tachyons in quantum mechanics is in the form of quantum fields. Quantum field theory, QFT, which is the theoretical framework that combines quantum mechanics with special relativity, describes how fields of energy interact with particles. In this view, the universe is filled with various fields, such as the electromagnetic field or the gravitational field, and particles are seen as excitations or disturbances within these fields. These fields are dynamic, constantly fluctuating, and give rise to the particles we observe. The behavior of these fields is governed by the principles of quantum mechanics, and tachyons, if they exist, would be a part of these fields, behaving in a way that is distinct from ordinary particles. In some versions of quantum field theory, tachyons are proposed as a possible feature of the vacuum itself. The quantum vacuum is not empty space, but a seething, fluctuating field of energy where virtual particles are constantly being created and annihilated. These virtual particles do not exist in the same way as real particles. Instead, they are short-lived and cannot be directly observed. However, they have measurable effects on the physical properties of the universe. Tachyons, if they exist, could be part of these vacuum fluctuations, temporarily popping in and out of existence in a way that would be difficult to detect. The presence of tachyons in the quantum vacuum could potentially influence the behavior of other particles and fields, leading to subtle changes in the way that forces like electromagnetism and gravity manifest. But how exactly would tachyons behave in a quantum field? If tachyons are faster than light, they would interact with the quantum fields in ways that ordinary particles cannot. One possibility is that they might affect the stability of the vacuum itself. In quantum field theory, the vacuum is typically considered to be in its lowest energy state, but the presence of tachyons could destabilize this state, leading to new phenomena. This idea is part of the broader concept known as vacuum instability, where the vacuum is not a perfectly stable background, but can undergo changes due to the presence of certain particles or fields. If tachyons were involved in this process, they could potentially alter the way that particles interact with one another and lead to the creation of new types of particles or fields. The potential role of tachyons in quantum mechanics also raises questions about how they might influence the fundamental forces of nature. One of the key goals of modern physics is to unify the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, coherent framework. This quest for a theory of everything has led to the development of theories such as string theory, which proposes that the fundamental particles of the universe are not point-like objects, but tiny vibrating strings of energy. In some versions of string theory, Tachyons are a natural feature, signaling instabilities in the theory that could lead to the discovery of new physical phenomena. Tachyons in the context of string theory are not just theoretical oddities, they're closely tied to the dynamics of the theory itself. In certain string models, tachyons are seen as a sign of an unstable vacuum, where the universe is in a state of flux and can evolve into a more stable configuration. This instability could have far-reaching consequences for our understanding of the cosmos, as it suggests that the universe is not a static, unchanging entity, but a dynamic and evolving system. The presence of tachyons in these models suggests that the universe may be more complex and malleable than we currently understand, with the potential for new, previously unimagined forms of matter and energy to emerge. Beyond the implications for the fundamental forces, tachyons also have the potential to influence the structure of spacetime itself. In quantum mechanics, spacetime is not a passive stage upon which events unfold. It is a dynamic, fluctuating entity that can bend, stretch, and ripple in response to the presence of mass and energy. The introduction of tachyons into the quantum description of spacetime could alter the way that spacetime behaves on the smallest scales. For example, tachyons might create ripples or distortions in the fabric of spacetime that could affect the motion of particles, the propagation of light, and even the structure of the universe itself. These effects would be subtle but potentially profound, revealing new aspects of the universe that are currently beyond our reach. Perhaps the most fascinating aspect of tachyons in quantum mechanics is the potential they offer for new kinds of quantum phenomena. Quantum mechanics is full of surprises, and tachyons could open the door to entirely new behaviors and interactions. If tachyons exist, they might be capable of interacting with other quantum particles in ways that we can't yet predict. These interactions could give rise to new kinds of quantum states, such as exotic matter or energy, with properties that are radically different from anything we've encountered before. This could lead to breakthroughs in areas such as quantum computing, where the ability to manipulate particles at the quantum level is key to creating more powerful and efficient technologies. Of course, much of this is still speculative. The existence of tachyons has not been confirmed, and the idea of faster-than-light particles remains an open question in modern physics. However, the potential role of tachyons in quantum mechanics highlights the flexibility and complexity of the quantum world. Quantum theory has already revolutionized our understanding of the universe, and the possibility of tachyons adds another layer of intrigue to this already fascinating field. Whether or not tachyons are ever discovered, their theoretical existence forces us to confront the limitations of our current understanding and pushes us to explore new ideas and possibilities in the realm of quantum physics. As we continue to explore the mysteries of the quantum world, the concept of tachyons remains one of the most exciting and puzzling challenges in modern physics. If they do exist, tachyons could unlock new dimensions of reality, offering us a deeper understanding of the universe and the forces that govern it. For now, they remain theoretical, but the very idea of faster-than-light particles forces us to rethink the boundaries of space, time, and the very nature of quantum mechanics. To fully appreciate the potential of tachyons and their impact on our understanding of the universe, it's crucial to examine the nature of the fields that could harbour these faster-than-light particles. In quantum field theory, QFT, which is the framework that describes how particles interact with fields, particles are not viewed as isolated entities. Instead, they are seen as excitations or disturbances in underlying fields that permeate all of space. These fields are dynamic, constantly fluctuating, and give rise to the particles we observe in the universe. Tachyons, if they exist, would be a specific type of particle associated with these quantum fields, exhibiting properties that set them apart from ordinary matter. To begin, let's first define what we mean by a quantum field. A field, in the context of QFT, is a fundamental entity that exists throughout space and can affect the behavior of particles. For example, the electromagnetic field is the field responsible for electromagnetic interactions, such as the forces between charged particles. Similarly, the gravitational field governs the force of gravity, and the Higgs field is responsible for giving particles mass. These fields are continuous, existing everywhere in space, and they interact with matter in various ways to produce the forces and particles that make up the universe. In QFT, particles are not thought of as discrete objects moving through space. Instead, they are seen as ripples or excitations in their respective fields. For instance, an electron is an excitation in the electron field, while a photon is an excitation in the electromagnetic field. These excitations move through space and interact with one another, giving rise to the phenomena we observe in the universe. Fields are not static, but rather they are dynamic and constantly fluctuating at the quantum level. Even in a perfect vacuum, quantum fields are never completely still. They are in a constant state of fluctuation, with virtual particles popping in and out of existence. Now, when we consider the nature of tachyonic fields, we need to understand how they would fit into this picture. Tachyons are theorized to be particles that exist in quantum fields with a specific property. They would have imaginary mass, which leads to their ability to exceed the speed of light. The key idea here is that these fields would behave differently from ordinary fields. While most fields are associated with particles that have real mass and move at subluminal speeds, tachyonic fields are linked to particles that travel faster than light and have imaginary mass. In the context of quantum field theory, a tachyonic field is typically one that is unstable. This instability arises from the fact that tachyons have imaginary mass. In quantum field theory, when a field has imaginary mass, it suggests that the field is not in its true stable ground state. Instead, the field is in a kind of false vacuum, where the system is temporarily unstable and could potentially transition to a more stable state. This idea of instability is closely tied to the concept of spontaneous symmetry breaking, which occurs when a system moves from a state of higher symmetry to one of lower symmetry. In the case of tachyonic fields, the instability could lead to the creation of new particles or fields, changing the underlying structure of the universe. The idea of tachyonic fields is not just a theoretical curiosity. It has real implications for our understanding of fundamental physics. One of the most important aspects of tachyonic fields is their connection to the early universe. During the infancy of the cosmos, when temperatures and energies were extremely high, the universe was in a state of constant flux. Fields, including tachyonic fields, were likely fluctuating and evolving rapidly, shaping the fundamental forces and particles that would later emerge. In fact, some theories suggest that the early universe may have been filled with tachyonic fields, and that their fluctuations could have played a key role in the formation of matter and energy as we know it. In certain versions of string theory, which posits that the fundamental building blocks of the universe are tiny, vibrating strings, tachyonic fields appear as a natural feature of the theory. In this context, tachyons are associated with unstable vacuum states, and their presence signals that the system is not in its lowest possible energy configuration. This concept of instability is not unique to tachyons. It is a feature of many systems in physics. However, the presence of tachyons in string theory suggests that the universe itself may have undergone a phase transition, moving from one state of symmetry to another, giving rise to the structure of the cosmos we observe today. One of the most interesting aspects of tachyonic fields is their potential to interact with other quantum fields. In quantum field theory, the interactions between different fields are what give rise to the forces and particles that make up the universe. For example, the electromagnetic field interacts with charged particles, giving rise to the force we know as electromagnetism. Similarly, the gravitational field interacts with mass and energy, creating the force of gravity. If tachyons exist, they would interact with the quantum fields in ways that ordinary particles cannot. Their faster-than-light motion and imaginary mass could lead to new types of interactions, potentially altering the way that particles and fields interact on the smaller scales. One possible effect of tachyonic fields is that they could influence the vacuum state of the universe. In quantum field theory, the vacuum is not truly empty. It is filled with fluctuating fields that constantly generate virtual particles. These virtual particles pop in and out of existence, but they are not directly observable. However, their effects can be measured, such as through the Casimir effect, which is a phenomenon that arises due to the fluctuations of the vacuum. Tachyons, if they exist, could contribute to these vacuum fluctuations, potentially altering the way that forces like electromagnetism or gravity behave on the quantum level. This could have profound implications for our understanding of the fundamental forces of nature and the behavior of particles at the smallest scales. Tachyonic fields also have the potential to influence the very nature of spacetime itself. In general relativity, spacetime is a dynamic entity that can bend and warp in response to the presence of mass and energy. The presence of tachyonic fields, with their faster-than-light particles, could create ripples or distortions in spacetime that affect the motion of particles and the propagation of light. These effects could be subtle but profound, revealing new aspects of the universe that are currently beyond our reach. If tachyons exist and interact with the fabric of spacetime, they could lead to new insights into the nature of gravity, time, and the fundamental structure of the cosmos. Despite all the fascinating possibilities that tachyonic fields present, it's important to note that the idea of tachyons remains highly speculative. No experimental evidence has yet been found to support the existence of tachyons, and the behavior of tachyonic fields remains largely theoretical. However, the theoretical framework surrounding tachyons provides valuable insights into the limits of our current understanding of the universe. If tachyons do exist, they could revolutionize our understanding of quantum mechanics, space-time, and the very nature of reality itself. And even if they remain purely hypothetical, the study of tachyonic fields challenges us to think beyond the boundaries of conventional physics and explore the possibilities of a universe that is far more complex and mysterious than we can yet imagine. To fully grasp the implications of tachyons and their place within the broader framework of physics, it's essential to understand the nature of their energy. In the context of classical mechanics and special relativity, the energy of a particle is intimately connected to its mass and speed. However, tachyons introduce a unique challenge to this conventional understanding. As particles that are theorized to travel faster than light, tachyons are expected to have a fundamentally different relationship with energy than particles that move at subluminal speeds. But what does this mean in practical terms? How do tachyons interact with energy, and what are they made of? In the realm of relativity, the energy of a particle is generally given by the famous equation E squared equals mc squared plus pc squared, where E is the total energy, m is the rest mass of the particle, c is the speed of light, and p is the relativistic momentum. This equation neatly links a particle's energy to its mass and velocity. For ordinary particles that travel at speeds less than the speed of light, this relationship works well. As an object moves faster, its momentum increases and its energy rises accordingly. However, for particles that move faster than light, such as tachyons, this equation requires a reinterpretation because tachyons are postulated to have imaginary mass, a property that does not fit neatly into this classical formula. The idea of imaginary mass, while perplexing at first, is crucial to understanding tachyons. In special relativity, mass plays a central role in determining how a particle behaves as it moves through space-time. For ordinary particles, the energy is determined by both their mass and their speed. However, for tachyons the situation is different. The term imaginary mass arises from the fact that the relativistic equations can be solved in such a way that a particle's mass can have a negative or imaginary value, which leads to some unusual consequences. Because tachyons have imaginary mass, they do not behave like ordinary particles when it comes to energy. As ordinary particles approach the speed of light, their energy increases without bound, and they require an infinite amount of energy to reach the speed of light. This is one of the key reasons why particles with real mass cannot exceed the speed of light. For tachyons, however, the situation is reversed. Instead of requiring more energy as they move faster, tachyons are theorized to gain more energy as they accelerate, and this energy increases as their speed approaches the speed of light and beyond. To understand this more clearly, it's important to look at how energy behaves for tachyons. For ordinary particles, as they approach the speed of light, their energy increases exponentially, and this requires a continuous increase in the energy supplied to them. In contrast, tachyons, which are theorized to always move faster than light, would have a different relationship with energy. Their energy would not behave in the same way as ordinary particles because they already possess imaginary mass. Their energy increases as their speed increases, unlike ordinary particles, where energy increases as they approach the speed of light. This means that tachyons would not require infinite energy to reach faster than light speeds. Instead, they would have more energy the faster they go, but they would not face the same kind of restrictions that particles with real mass do. This unusual relationship between energy and speed is one of the key features that makes tachyons such an interesting theoretical concept. The fact that tachyons are hypothesized to always travel faster than light means that their energy must behave differently from anything we encounter in our everyday experiences. If tachyons exist, their energy would be tied to their speed in a way that defies the normal rules of relativity. This could open up new possibilities for understanding the fundamental nature of energy and its relationship to spacetime. Now, let's consider what tachyons are made of. In the context of quantum field theory, all particles are seen as excitations or ripples in underlying quantum fields. For example, photons are excitations in the electromagnetic field, and electrons are excitations in the electron field. Tachyons, if they exist, would also be excitations in a specific field, known as the tachyonic field. This field would be a type of quantum field that is associated with particles that always move faster than light. The presence of tachyons in this field would suggest that the field itself is unstable, in the sense that it is not in its true ground state, but rather in a false vacuum. This instability is a key feature of tachyonic fields, as we discussed in the previous section. The energy of tachyons would be tied to the fluctuations in this field, and the faster the tachyon moves, the greater its energy. In string theory, tachyons play a particularly important role. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings can exist in multiple dimensions, and their vibrations determine the properties of the particles they give rise to. In some versions of string theory, tachyons are an intrinsic feature of the theory. When tachyons appear in these models, they signal an instability in the vacuum state of the theory, a state of false symmetry. This instability is significant because it suggests that the universe could undergo a transition to a more stable state, and the presence of tachyons could be a sign of such a transition. The energy of tachyons in string theory is tied to this process of symmetry breaking. As tachyons interact with the field, they could trigger the breakdown of symmetries in the system, leading to the creation of new states of matter and energy. This process could have profound implications for our understanding of the early universe and the evolution of the cosmos. The presence of tachyons in string theory indicates that the universe is not in a static, unchanging state, but rather is constantly evolving, with new particles and forces emerging as the system moves through different phases. The idea that tachyons are connected to the very fabric of spacetime itself through their interactions with the tachyonic field also raises questions about how energy behaves on the most fundamental scales. Tachyons would not just represent faster-than-light particles, but could also help us understand the deeper mechanisms that govern the energy of the universe. By studying how tachyons interact with quantum fields and how their energy behaves, we may gain new insights into the relationship between matter, energy, and space-time. But even though tachyons are still theoretical and have not been directly observed, their possible existence challenges our conventional notions of energy and mass. Tachyons suggest that energy is not just a static, measurable quantity, but something more dynamic, something that may behave in unexpected ways. If tachyons can exist and their energy behaves as predicted, it would mean that our understanding of how particles interact with energy, mass, and space-time must be revised. The study of tachyons forces us to confront the possibility that there are more dimensions to reality than we currently comprehend, and that the fundamental properties of energy might be far more complex than we imagine. In conclusion, tachyons present a fascinating challenge to our understanding of energy, mass, and space-time. While we may not yet have direct evidence of their existence, the theoretical implications of tachyons push the boundaries of our knowledge and force us to reconsider everything we know about the universe. If tachyons are real, they could open up new dimensions of physics, allowing us to explore new forms of energy, new interactions between particles, and perhaps even new laws of nature. For now, tachyons remain a tantalizing possibility, but they continue to inspire new ideas and theories that may one day change the way we think about the very nature of the universe itself. The possibility of faster-than-light communication is one of the most exciting and mind-boggling aspects of the theoretical existence of tachyons. If tachyons exist and can travel faster than light, they could provide a means of communication that bypasses the conventional limits imposed by the speed of light. This idea, although purely theoretical, opens up new dimensions of possibility for how we might communicate across vast distances and even, perhaps, across different points in time. One of the most intriguing thought experiments that explores the potential of faster-than-light communication via tachyons is the concept of the tachyonic antitelephone. Proposed by physicist Gerald Feinberg in the 1960s, the tachyonic antitelephone is a theoretical device that would use tachyons to send information faster than light, with the added twist that this information could potentially be transmitted backward in time. At the core of the tachyonic antitelephone is the idea that tachyons, by their very nature, could violate the standard rules of causality. As we've discussed previously, causality is the principle that cause must precede effect, the foundation of our understanding of how events unfold in the universe. If tachyons can travel faster than light, they could potentially allow for a reversal of this flow, allowing effects to precede causes. This presents both an opportunity and a paradox. If information could be sent faster than light, it might be received before it's even transmitted, leading to the possibility of time loops and causality violations. The concept of the tachyonic antitelephone is based on the idea that, because tachyons move faster than light, signals sent via tachyons could potentially reach their destination before they were even sent, creating a situation where the receiver would receive the message before the sender transmits it. This would mean that in theory one could send a message to the past, communicating with someone in an earlier time. While this is a fascinating concept from a theoretical perspective, it also raises a number of troubling questions about the nature of time and the consistency of events. To visualize how the tachyonic antitelephone might work, imagine a scenario where two individuals, Alice and Bob, want to communicate over vast distances. Using conventional communication methods, Alice would send a signal to Bob, and it would take time for the signal to travel from one point to the other. The speed of light acts as a natural barrier, preventing information from reaching its destination faster than light can travel. But in the case of the tachyonic antitelephone, Alice could send a signal using a tachyonic particle, which would travel faster than light, potentially arriving at Bob's location before Alice even transmits it. From Bob's perspective, the message would appear to come from the future, even though Alice sent it from the past. The implications of this are far-reaching. If information could travel backward in time, it could lead to a breakdown of the principle of causality. events that we perceive as unfolding in a fixed order could become unhinged, with effects occurring before their causes. This introduces the possibility of paradoxes, such as the famous grandfather paradox. In this scenario, a time traveller could go back in time and prevent an event from occurring that would have led to their own existence, creating a loop where the cause and effect are reversed. The tachyonic anti-telephone would open up the possibility for such paradoxes, challenging our fundamental understanding of the flow of time and the structure of the universe. While the tachyonic anti-telephone is purely theoretical and has not been demonstrated in practice, it raises important questions about the nature of time, information, and the laws of physics. Could the use of tachyons for communication represent a path to overcoming the limitations of the speed of light? Could it provide a means of connecting distant points in the universe instantaneously? Or could it, as the tachyonic anti-telephone suggests, lead to the breakdown of causality and the creation of paradoxes? There are several key challenges to the concept of the tachyonic anti-telephone. First, the very existence of tachyons is still hypothetical. No experimental evidence has been found to confirm that tachyons exist or can be detected. Without direct evidence of their existence, it's impossible to build a communication system based on tachyons. Second, even if tachyons do exist, there are significant hurdles to overcome in order to use them for communication. Tachyons are theorized to interact weakly with matter, meaning that detecting them or manipulating them in a controlled way would be incredibly difficult. In addition, the idea of sending a message back in time raises profound questions about the stability and consistency of the universe. If tachyons can travel backward in time, could we alter the past? If we can change the past, how do we prevent paradoxes that might arise from such changes? Despite these challenges, the concept of the tachyonic anti-telephone remains an intriguing possibility, one that forces us to reconsider our understanding of time and space. In the world of quantum mechanics and relativity, we are already accustomed to the idea that time is not an absolute, unchanging quantity. The flow of time is relative and can be influenced by speed, gravity, and the curvature of spacetime. The possibility of tachyons, which could potentially exceed the speed of light, adds a new layer of complexity to our understanding of time, suggesting that it may not be as fixed and rigid as we once thought. Tachyons may not only offer a way to communicate faster than light, they could fundamentally alter the way we think about causality, time, and even the nature of reality. To further complicate matters, if tachyons can be used to send messages backward in time, the concept of communication itself could be altered. Traditional communication is based on a linear flow of information from one point to another with a clear cause, the sender, and effect, the receiver. But with tachyons, the cause and effect could become entangled, with the message appearing to arrive before it is sent. This creates a scenario where information could circulate in loops, and the usual distinction between the past, present, and future might no longer apply in the same way. If we can communicate with the past, we might be able to change the course of events, but how would that impact the future? What happens to the timeline we've experienced if the events leading up to it can be rewritten? Ultimately, the tachyonic anti-telephone is a powerful thought experiment because it invites us to reconsider the fundamental nature of time, causality, and communication. It challenges the very structure of reality as we know it, and forces us to ask whether the boundaries of the universe are as rigid as we once believed. While the tachyonic anti-telephone may remain firmly in the realm of theoretical physics for now, its implications are far-reaching, and may provide a glimpse into new frontiers of science, where the flow of information is not limited by the speed of light, and where time itself can be manipulated in ways we have yet to fully understand. While tachyons are a theoretical concept within the realm of physics, their influence has extended far beyond the confines of academic research. These mysterious, faster-than-light particles have made their mark on popular culture, from science fiction stories to blockbuster films and television shows. In many ways, tachyons have bridged the gap between the abstract world of theoretical physics and the vivid, imaginative landscapes of speculative fiction. Yet, despite their origins in the world of science, they have taken on a life of their own in fiction, often serving as a narrative device that explores the limits of time, space, and the possibilities of faster-than-light travel. In science fiction, tachyons are often used to explore the boundaries of reality, time, and communication. The idea of particles that can break the speed limit of the universe opens up endless possibilities for storytelling, especially in narratives involving time travel, parallel universes, and instantaneous communication. One of the key features of tachyons in these stories is their ability to transcend the conventional limitations of space and time, allowing characters to travel through time or communicate across vast distances without the constraints imposed by the speed of light. In many ways, tachyons have become synonymous with the idea of breaking the rules of the universe, and their use in fiction reflects the desire to push the boundaries of what we think is possible. One of the most famous examples of tachyons in popular culture is in the Star Trek franchise. In the Star Trek universe, tachyons are frequently referenced as part of the technology used to communicate across vast distances or to explain unusual phenomena. For example, in the Star Trek The Next Generation episode, The Nth Degree, tachyons are used to enable the ship's communication system to function over vast distances, playing a role in the story's exploration of advanced technology and faster-than-light communication. Additionally, in Star Trek Voyager, tachyon-based technology is employed to detect and manipulate anomalies in space-time. These appearances highlight the potential for tachyons to be used as tools for navigating the vast and mysterious expanse of the universe, from manipulating time to interacting with strange cosmic phenomena. Beyond Star Trek, tachyons have made appearances in a variety of other science fiction works. In the Doctor Who series, for example, tachyons are referenced as a possible means of communication that could span across time and space. In the episode The Sound of Drums, tachyons are used to explain how time can be manipulated, a key theme of the show, where the laws of physics are often bent to fit the narrative of time travel and alien intervention. Similarly, tachyons appear in the Flash TV series, where they are used to explain the behaviour of particles moving faster than light and their connection to time travel and alternate realities. In these examples, tachyons often serve as the catalyst for the plot, facilitating the character's ability to transcend normal limitations and explore the depths of time, space, and reality itself. Tachyons also appear in the realm of video games, where their ability to move faster than light is often used as a plot device or gameplay mechanic. In the Mass Effect series, for example, the concept of faster-than-light travel is central to the game's setting, and while tachyons are not explicitly named, the idea of manipulating particles or energy to achieve faster-than-light travel is a key element in the game's fictional science. Similarly, in Star Wars, Knights of the Old Republic, faster-than-light travel is made possible by the use of a technology known as hyperdrive, which, like tachyons in theoretical physics, allows characters to traverse vast distances almost instantaneously. While tachyons themselves may not be directly mentioned, the underlying concept of breaking the speed limit is a consistent theme in science fiction, and it often draws upon the idea of particles or technology that can transcend the speed of light. In addition to these fictional depictions, tachyons have also made their way into popular media as part of broader narratives involving the future of physics and space exploration. For instance, in The Hitchhiker's Guide to the Galaxy, Douglas Adams references the idea of faster-than-light travel as part of the quirky, imaginative universe he created. Though tachyons themselves are not specifically mentioned, the concept of bending or breaking the speed of light is woven into the fabric of the story, as characters explore new dimensions and engage in time-bending adventures. The use of science fiction to tackle the question of what might be possible beyond the speed of light reflects society's broader curiosity about the fundamental limits of the universe and the potential for breakthroughs in our understanding of space and time. While these fictional depictions often take liberties with the scientific principles underlying tachyons, they serve a deeper cultural purpose. Tachyons, like many other theoretical concepts in science, provide a way for us to explore our collective imagination and contemplate the possibilities of a universe that is far stranger and more complex than we can currently understand. They provide a narrative tool that allows writers, filmmakers, and game developers to stretch the limits of what we think is possible, creating stories that challenge our perceptions of time, space, and reality. In this way, tachyons have become more than just a theoretical concept in physics. They have become a symbol of possibility, of breaking boundaries, and of exploring the unknown. Despite their widespread use in science fiction, it's important to remember that tachyons remain purely theoretical in the realm of real-world physics. No experimental evidence has yet been found to support their existence, and the idea of faster-than-light particles is still a subject of intense debate among physicists. However, the idea of tachyons has inspired real scientific inquiry and has pushed physicists to consider new possibilities in the field of theoretical physics. In some respects, the way tachyons have been depicted in popular culture reflects the fascination with ideas that challenge the conventional boundaries of science, ideas that inspire wonder, curiosity, and the desire to explore what might lie beyond the limits of human understanding. While tachyons in science fiction may operate outside the confines of the laws of physics as we understand them, they represent a symbolic bridge between the world of theoretical science and the world of human imagination. They are part of a broader cultural narrative that reflects our ongoing quest to understand the fundamental nature of the universe. Whether or not tachyons are ever discovered or proven to exist, they will continue to play a key role in inspiring scientific inquiry, creative storytelling, and our ongoing exploration of the mysteries of the cosmos. While tachyons are still purely theoretical particles in the realm of physics, their potential applications, if they were ever proven to exist, could radically transform our understanding of the universe and revolutionize technology. The possibility of faster-than-light particles introduces a host of speculative uses in fields ranging from communication and computing to space exploration and even time manipulation. Although the idea of tachyons remains unproven, exploring the potential applications of these particles opens up a fascinating window into the future of physics and technology. One of the most intriguing applications of tachyons is their potential to revolutionize communication. In today's world, communication is governed by the speed of light, with data traveling through fiber optics, satellites, and radio waves, all constrained by the ultimate speed limit of the universe. The fastest communication systems currently in use, such as fiber optic cables, transmit information at speeds that are still far slower than the speed of light. This speed limit is a fundamental barrier to instant communication over long distances. However, if tachyons exist and can be manipulated, they could theoretically enable communication that transcends the speed of light, effectively eliminating the delay associated with current communication technologies. This faster-than-light communication could have profound implications for a variety of fields. For example, in space exploration, the distances between Earth and distant spacecraft are vast, and communication with astronauts on missions to Mars or beyond can take anywhere from minutes to hours, depending on the relative positions of the planets. If tachyon-based communication were possible, this delay could be reduced to nearly zero, enabling real-time communication between Earth and spacecraft, making space missions more efficient and safer. The ability to communicate instantaneously with distant space probes or colonies could be invaluable in the event of emergencies or for sending time-sensitive instructions or data. Furthermore, tachyons could potentially enable a new form of global communication, where data could be transmitted instantaneously between any 2 points on Earth, regardless of distance. This would render current systems like fiber optics, satellites, and the internet obsolete, creating a world where information flows without delay. Businesses, governments, and individuals could exchange information in real time, without waiting for signals to travel across continents or oceans. This application could extend beyond just communication, as it could enable the rapid exchange of massive data sets, making everything from cloud computing to medical diagnostics and research more efficient. In addition to communication, tachyons could also have groundbreaking applications in the field of computing. Quantum computing, which exploits the principles of quantum mechanics to perform computations that are far more efficient than classical computers, is already pushing the boundaries of what is possible in terms of speed and computational power. Tachyons, if they exist, could play a significant role in the future of quantum computing. Their ability to move faster than light and potentially interact with quantum fields could open up new methods of data processing and information transfer. Tachyonic particles might even be used to create quantum entanglement or teleportation systems, which are key components of quantum communication networks. If tachyons could be harnessed for quantum computing, they could lead to the development of computational systems far more powerful than anything we can currently imagine, capable of solving problems that are beyond the reach of classical computers. Tachyons could also have potential applications in the field of energy. In conventional physics, energy is linked to mass, and the speed at which energy is transferred or transported is constrained by the speed of light. If tachyons exist, they could provide a new way of transferring energy across vast distances. For example, in power generation and transmission, tachyonic energy transfer could theoretically enable the instantaneous transport of energy from one point to another without the need for long-distance cables or infrastructure. This could lead to the development of highly efficient, virtually lossless energy transmission systems, making the global energy grid far more efficient and reliable. Another possible application of tachyons could be in the area of time manipulation or time travel. While this might sound like science fiction, the concept of tachyons and their ability to exceed the speed of light raises the possibility of using them to travel backward in time, at least theoretically. In the realm of theoretical physics, time travel is often discussed in terms of wormholes or closed time-like curves, which allow for the possibility of traveling to the past or future. If tachyons could be manipulated to move backward in time, they might offer a method for communication or even travel to different points in history. While time travel remains a highly speculative and controversial idea, the exploration of tachyons could provide new insights into the fundamental nature of time and the potential for manipulating it. The idea of time manipulation also leads to the speculative concept of tachyon-based time machines. If tachyons can travel backward in time, it might be possible, in theory, to use them to create a machine that could send information or even matter to a previous point in time. While this application is, at best, a distant and highly speculative possibility, it highlights the profound impact that tachyons could have on our understanding of the universe. Time travel, though currently relegated to the realm of science fiction, is a subject of ongoing interest among physicists, and tachyons could be a key to unlocking the mysteries of time and its manipulation. In the realm of fundamental physics, the discovery of tachyons could also provide new insights into the nature of the universe itself. The idea of faster-than-light particles challenges our current understanding of space, time, and causality, and their discovery could lead to new theories and models that explain the origins and structure of the cosmos. Tachyons could potentially be linked to phenomena such as dark matter, dark energy, or the early stages of the universe's formation, offering clues to the deepest mysteries of the cosmos. In this sense, the discovery of tachyons could pave the way for a new era of exploration, where the boundaries of space and time are no longer seen as immutable, but as dynamic, flexible features of the universe that can be understood and manipulated. Despite the speculative nature of these applications, the mere possibility that tachyons could exist and be harnessed for practical use serves as a reminder of the endless potential that lies in the uncharted territories of science. Even if tachyons never become a part of our technological future, their exploration helps us push the boundaries of what we know about the universe and challenges us to think beyond the conventional limits of physics. In conclusion, the potential applications of tachyons are vast and varied, spanning fields like communication, computing, energy, and even time manipulation. While we have yet to discover any experimental evidence that confirms the existence of tachyons, their theoretical implications provide an exciting glimpse into the future of physics and technology. Whether or not tachyons are ever proven to exist, they inspire us to imagine a future where the laws of the universe can be stretched, broken, and redefined, opening up new possibilities for human progress and discovery. Tachyons, as theoretical particles that are hypothesized to travel faster than the speed of light, offer a fascinating realm of possibilities that could challenge the very foundations of modern physics. Yet, despite their intriguing potential, research into tachyons is fraught with significant challenges and controversies. These difficulties range from the very existence of tachyons themselves to the complexities of how they might interact with other particles and forces in the universe. Although the concept of tachyons has been proposed within the frameworks of special relativity and quantum field theory, no experimental evidence has yet been found to confirm their existence, and this lack of empirical support has led to considerable debate among physicists. One of the fundamental challenges in tachyon research is the very question of whether tachyons exist at all. While theoretical models suggest that faster-than-light particles could exist, there has been no direct observation of such particles in nature. The idea of particles that move faster than light is in direct opposition to the well-established principles of special relativity, which posits that the speed of light is the ultimate speed limit for any particle with real mass. The lack of experimental evidence supporting the existence of tachyons has led some physicists to question whether they are anything more than a mathematical curiosity or a theoretical artifact that doesn't correspond to the physical world. One of the key reasons why tachyons have yet to be observed is their predicted behavior in the quantum realm. Tachyons are theorized to interact with quantum fields in ways that are vastly different from ordinary particles. For example, in quantum field theory, particles are typically excitations or disturbances in their respective fields. However, tachyons are proposed to have imaginary mass, which means they would not behave in the same way as particles with real mass. This raises the question of how tachyons might interact with other particles or fields, and how we might detect their presence. If tachyons do exist, their interactions with matter and energy may be weak and subtle, making them difficult to detect using current experimental methods. Another challenge in tachyon research is the theoretical nature of their interactions with spacetime. According to special relativity, particles that exceed the speed of light would violate the principles of causality, potentially leading to paradoxes where effects precede causes. If tachyons were to travel faster than light, they might create situations where the sequence of events is reversed, challenging the very structure of time and space. This raises significant questions about the stability of the universe and the laws that govern it. How can we reconcile the existence of tachyons with our understanding of causality and the smooth, continuous flow of time? The potential for tachyons to disrupt the fundamental principles of physics has made them a controversial subject in the scientific community, with some physicists arguing that they represent a logical impossibility, and others speculating that they could open the door to new, unknown aspects of the universe. The issue of tachyonic instability is another point of contention in tachyon research. In quantum field theory, the existence of tachyonic fields is often associated with instability, specifically with the concept of spontaneous symmetry breaking. Tachyons are typically viewed as an indication that a system is not in its lowest energy state, but is instead in a false vacuum. This false vacuum is thought to be an unstable state that could eventually decay, leading to the formation of a more stable vacuum. While this idea is consistent with some models in physics, the concept of tachyonic instability is controversial in its own right. Some theorists argue that tachyonic fields might not lead to any meaningful physical processes, while others speculate that they could have profound implications for our understanding of the universe, particularly in the context of the early universe and the formation of fundamental forces. Another point of contention in tachyon research is the potential implications for time travel and causality. If tachyons can travel faster than light and even move backward in time, they could introduce paradoxes and contradictions that are difficult to reconcile with our current understanding of the laws of physics. Time travel, a concept that has fascinated scientists and philosophers alike, is fraught with logical difficulties. The idea that particles could move through time in ways that violate the usual cause and effect relationship challenges our basic notions of how events unfold in the universe. Could tachyons create time loops? Could they lead to situations where the past, present and future are no longer distinct? These are questions that have yet to be fully answered, and they have made tachyon research both exciting and controversial. While tachyons may offer a theoretical path to time travel, their potential to destabilize the fabric of reality itself makes them a highly contentious subject in physics. Moreover, the very concept of faster-than-light particles raises questions about the limits of physics itself. Special relativity, one of the cornerstones of modern physics, asserts that the speed of light is the ultimate speed limit. This principle has been confirmed through countless experiments and observations. The existence of tachyons, if proven, would challenge this foundational aspect of relativity. It would suggest that the universe is not governed by the same laws we have come to rely on, and that our understanding of space, time, and energy may be incomplete. This uncertainty about the limits of physics has led some scientists to view tachyons as a concept that may ultimately be disproven, while others argue that their existence could signal the need for a more expansive theory of the universe, one that goes beyond the confines of special and general relativity. Another major obstacle in tachyon research is the difficulty in testing their existence. Tachyons, by their very nature, would interact weakly with matter, making them difficult to detect through conventional means. Unlike other particles that interact with electromagnetic fields and can be detected by particle accelerators, tachyons would likely not leave the same kind of trace or signature that scientists can easily measure. This makes it challenging to design experiments that could confirm their existence. Theories involving tachyons are often speculative and indirect, relying on mathematical models and simulations rather than direct experimental data. Until more advanced detection methods or new technologies are developed, it is unlikely that tachyons will be observed in a laboratory setting anytime soon. Despite these challenges and controversies, tachyons remain an important area of research in theoretical physics. Their potential to unlock new insights into the nature of space, time, and the fundamental forces of the universe keeps scientists intrigued by the possibilities. The exploration of tachyons forces us to question the very limits of our current understanding and to push the boundaries of what is possible within the realm of physics. Whether or not tachyons are ever discovered, the ideas surrounding them continue to inspire physicists to think more deeply about the nature of the universe and to explore the mysteries that still lie beyond our reach. In conclusion, the study of tachyons is fraught with significant challenges, from the question of their existence to the implications they have for time, causality, and the structure of spacetime. While the theoretical framework of tachyons is based on well-established principles of relativity and quantum field theory, the lack of experimental evidence, the potential for paradoxes, and the difficulty of detecting such particles have made them a controversial and highly speculative area of research. Despite these challenges, tachyons continue to capture the imagination of physicists, offering a glimpse into a universe that may be far stranger and more complex than we currently understand. The question of why we haven't found tachyons yet, despite their fascinating theoretical implications, speaks to the very heart of why they remain such a tantalizing mystery in the world of physics. While tachyons have been proposed within the frameworks of special relativity, quantum mechanics, and even string theory, their existence remains unproven. The theoretical models that suggest their presence are elegant and intriguing, but they also raise profound questions about the nature of reality and our ability to detect particles that may defy conventional understanding. So, why have we not been able to observe tachyons, despite decades of research and technological advancements? One of the fundamental challenges in finding tachyons is their predicted interaction. or lack thereof, with ordinary matter. In the framework of quantum field theory, particles are viewed as excitations in underlying fields. These particles interact with one another through various forces, and it is these interactions that allow us to observe their presence. For example, photons interact with the electromagnetic field, and we can detect their presence through the effects they have on charged particles. However, tachyons are theorized to have an imaginary mass, which leads them to behave in ways that differ significantly from ordinary particles. One of the most striking features of tachyons is that they would not interact strongly with the electromagnetic field, which means that detecting them through conventional means, such as particle detectors, would be incredibly difficult. Without strong interactions with matter, tachyons would leave few detectable traces, making them elusive and nearly impossible to observe directly. This lack of interaction with ordinary matter is one reason why tachyons have not been observed experimentally. In most particle physics experiments, scientists look for evidence of particles by detecting the interactions they have with other particles or fields. For example, when high-energy particles collide in a particle accelerator like the Large Hadron Collider, scientists look for signals that indicate the creation of new particles or the interaction of particles with existing fields. The fact that tachyons are predicted to have weak interactions with other particles means that their presence may not cause the kinds of observable effects that typical particles do. This makes it difficult, if not impossible, to detect tachyons using traditional experimental methods, such as those employed in particle accelerators or other large-scale physics experiments. Additionally, the nature of tachyons themselves presents a challenge. Tachyons are theorized to travel faster than light, which places them outside the realm of direct observation using conventional tools. The speed of light is, after all, a fundamental limit in the universe, and the very concept of something exceeding this limit seems counterintuitive to our understanding of physics. While special relativity allows for the theoretical possibility of tachyons, it also creates paradoxes, particularly when it comes to causality and the flow of time. If tachyons can exceed the speed of light and travel backward in time, how can we account for their interactions with the rest of the universe? Could their very existence break the consistency of physical laws, leading to contradictions that make them impossible to detect? These theoretical challenges, while fascinating, make the detection and study of tachyons a highly complicated pursuit. Furthermore, the role of tachyons in quantum field theory and string theory is still not fully understood. In quantum field theory, tachyons are often associated with instabilities in the vacuum state of certain fields, signifying that the system is in a false vacuum and could undergo a phase transition to a more stable state. However, whether these vacuum instabilities have physical consequences or whether they are merely mathematical artifacts is still an open question. In string theory, tachyons appear in certain models as signs of an unstable vacuum, but these models are still speculative and highly abstract. If tachyons exist, they may be part of a deeper, more complex framework of physics that we have yet to fully understand or observe. Another reason we have not detected tachyons may lie in the limitations of our current detection technologies. Our most advanced instruments, such as particle accelerators and high-resolution telescopes, are designed to observe particles that interact with ordinary matter. These instruments are finely tuned to detect known particles, such as electrons, protons, and photons, which have well-defined interactions with electromagnetic fields or other forces. Tachyons, by contrast, are theorized to have an entirely different set of properties, including weak or non-existent interactions with most forms of matter. This means that current technologies may simply be ill-equipped to detect tachyons or to observe their effects. New experimental techniques or innovations in detection might be necessary to identify tachyons should they exist. For example, scientists might need to develop instruments that can detect more subtle interactions, or perhaps look for indirect evidence of tachyons through their effects on quantum fields or spacetime itself. The absence of direct evidence for tachyons is also tied to the broader issue of theoretical uncertainty. While tachyons are a natural consequence of certain equations in quantum field theory and special relativity, their existence remains speculative because the relevant physical models themselves are not fully developed or tested. For example, some physicists argue that tachyons may be confined to specific theoretical contexts, such as high-energy particle interactions or the early moments of the universe, where the conditions necessary for their existence could occur. In this sense, tachyons may never be observable in the same way that we observe particles in our everyday experience. The models that predict their existence often involve exotic conditions or extreme environments, such as those that existed in the first moments after the Big Bang, making it difficult to replicate these conditions in laboratory experiments or to observe them in nature. Moreover, the theoretical challenges associated with tachyons have led some scientists to question whether they are a real physical phenomenon at all. Some researchers believe that tachyons may be an artifact of mathematical models rather than an actual part of the universe's physical structure. In this view, tachyons could represent an abstraction, a theoretical tool that helps solve equations or explain certain phenomena in quantum field theory, but not something that corresponds to actual particles in nature. If this is the case, it would explain why we have never detected tachyons despite the predictions of various theoretical models. The absence of experimental confirmation is not the only reason for skepticism about tachyons. There are also philosophical and conceptual concerns. The existence of faster-than-light particles challenges our fundamental understanding of space, time, and causality. If tachyons can travel faster than light and potentially reverse the flow of time, this would force us to reconsider many of the basic principles of physics. Some physicists argue that the very idea of particles that can break the speed of light is incompatible with the established laws of physics, and that tachyons should therefore be treated with caution. The challenges associated with tachyons force us to think about the limits of scientific inquiry itself. Are we asking the right questions about the universe? And do we truly understand the nature of space and time? In conclusion, the primary reason why we have not found tachyons is the theoretical and experimental challenges that surround them. Their weak interactions with matter, their connection to unstable quantum fields, and their violation of causality make them elusive and difficult to detect. Moreover, the uncertainty surrounding their theoretical foundations and the limitations of our current detection methods make it unlikely that we will observe tachyons anytime soon. Yet, despite these challenges, the pursuit of tachyon research remains an important endeavour. Whether or not tachyons exist, their study forces us to confront the deepest questions in physics, pushing the boundaries of our knowledge and inspiring new ways of thinking about the universe. As we continue to explore the nature of space, time, and fundamental forces, the search for tachyons may one day reveal new insights that will reshape our understanding of the cosmos. Tachyons, the hypothetical particles that exceed the speed of light, stand at the intersection of speculative physics and the unknown. Although their existence remains unproven, the theoretical exploration of tachyons has already prompted a re-evaluation of some of the most fundamental principles of physics. The potential discovery of tachyons would not only reshape our understanding of space, time, and causality, but could also open entirely new chapters in the study of the universe. But what would the future of physics look like if tachyons were proven to exist? How might they influence the development of scientific theory and technology in the coming years? First and foremost, the discovery of tachyons would represent a groundbreaking moment in physics, challenging the current understanding of relativity and its dominance in modern science. The speed of light, as formulated in Einstein's theory of special relativity, is a fundamental constant in our understanding of space and time. It serves as the ultimate speed limit for all objects with mass. If tachyons were found to exist, they would represent a fundamental violation of this principle. This would force physicists to rethink key aspects of Einstein's theory, and possibly revise or extend it to accommodate faster-than-light particles. One possibility is that tachyons could provide the foundation for a new framework of physics that unifies relativity with quantum mechanics. While relativity successfully explains the behavior of objects at large scales, such as planets and galaxies, it does not fully account for the behavior of particles on the smallest scales. Quantum mechanics, on the other hand, excels at describing particles at microscopic scales, but it struggles to incorporate gravity and the curvature of spacetime. Tachyons, as faster-than-light particles, might be able to bridge the gap between these two paradigms, offering a new way to integrate the principles of relativity with quantum mechanics. This integration could lead to a deeper understanding of the fundamental forces that govern the universe. For instance, the interaction between tachyons and quantum fields might provide insight into the nature of dark matter and dark energy, two mysterious components of the universe that make up the majority of its mass and energy, but remain largely invisible to current detection methods. Some theorists have suggested that tachyons could be related to the dark energy that accelerates the expansion of the universe, or that their existence could offer clues to the underlying structure of the cosmos. Moreover, the theoretical study of tachyons could also offer new insights into the early universe. During the first moments after the Big Bang, the universe was in an extremely high-energy state, and many of the particles and forces we observe today would have been in their infancy. Tachyons, as hypothetical particles that could exceed the speed of light, might have played a role in shaping the early universe, potentially influencing the formation of matter, energy, and the forces that govern their interactions. Understanding how tachyons fit into the cosmological model could help to unlock the mysteries of the Big Bang and the evolution of the universe in its earlier stages. The discovery of tachyons could also fundamentally alter our understanding of time itself. In special relativity, time is not an absolute constant, but is instead relative to the observer's motion through space-time. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. If tachyons exist and can move faster than light, their potential to travel backward in time could lead to entirely new ways of thinking about the flow of time, causality, and the possibility of time travel. The implications of this would extend far beyond theoretical physics, influencing not only the foundations of science, but also philosophy, ethics, and even the way we think about the future. In addition to these profound shifts in our understanding of the universe, the practical applications of tachyons could be revolutionary. As discussed in previous sections, the possibility of faster-than-light communication, time manipulation, and energy transfer could fundamentally transform technology. If tachyons were harnessed, they could lead to the development of technologies that would allow us to communicate instantaneously over vast distances, potentially revolutionizing telecommunications and global networking. Similarly, tachyon-based systems could enable new forms of energy transfer that are far more efficient than current methods, potentially leading to breakthroughs in energy storage and distribution. One of the most exciting potential applications of tachyons is in the field of space exploration. Currently, interstellar travel is constrained by the vast distances between stars and the limitations of conventional propulsion technologies. Even with the fastest spacecraft available, it would take tens of thousands of years to reach the nearest star. If tachyons were discovered and harnessed, they could provide a means of communication and travel that transcends the speed of light, making interstellar journeys more feasible and efficient. This could dramatically expand the possibilities for humanity's exploration of the cosmos, allowing for faster communication with distant space probes and perhaps one day, even enabling faster-than-light travel for humans. The discovery of tachyons could also lead to new research avenues in fields like quantum computing, where the potential for faster-than-light information transfer could radically enhance computational power. Quantum computing, which uses the principles of quantum mechanics to perform computations, already promises to outperform classical computers in certain tasks. If tachyons could be integrated into quantum systems, they might allow for even faster data processing and transmission, pushing the boundaries of what quantum computers can achieve. However, despite all these potential advancements, the discovery of tachyons would also raise significant ethical and philosophical questions. Time travel, for example, poses the risk of altering the course of history, leading to paradoxes and unintended consequences. The ability to communicate faster than light or manipulate time could create power imbalances, with some entities potentially gaining access to information or technologies far beyond the reach of others. As with any new discovery, the potential benefits of tachyon-based technologies would need to be balanced with careful consideration of the risks and ethical implications. Another challenge that would accompany the discovery of tachyons is the need for new experimental tools and techniques. Tachyons, by their very nature, are hypothesized to interact weakly with other forms of matter, making them extremely difficult to detect. This presents a major obstacle to confirming their existence. Current technologies such as particle accelerators and advanced telescopes are designed to detect particles that interact with electromagnetic fields or other forces. Tachyons, however, are theorized to interact in ways that would not leave obvious traces, making them elusive targets for detection. Developing the technology to detect tachyons, if they exist, would be a monumental challenge that could require entirely new experimental methodologies. Despite these challenges, the pursuit of tachyon research holds immense promise. Whether or not tachyons are ever discovered, their exploration pushes the limits of our understanding and encourages us to think more deeply about the nature of the universe. Theoretical physics has always been driven by the pursuit of ideas that challenge the status quo, and tachyons are a perfect example of this. They represent the unknown, the uncharted territory of science where the rules of physics may not be as fixed as we once thought. The discovery of tachyons, or even the theoretical insights gained from their study, could reshape the future of physics in ways that we're only beginning to imagine. In conclusion, tachyons have the potential to change the future of physics in profound ways. If they exist, they could lead to breakthroughs in our understanding of space, time, and the fundamental forces of the universe. Their practical applications in communication, energy transfer, space exploration, and quantum computing could revolutionize technology and expand the possibilities of human progress. Even if tachyons remain theoretical, their study pushes the boundaries of science and inspires new ways of thinking about the cosmos. The future of physics, shaped by the search for tachyons, holds the promise of a deeper understanding of the universe and the potential to unlock new realms of scientific discovery. As we reach the end of our exploration of tachyons, it becomes clear that their theoretical existence opens up an almost infinite array of possibilities. Possibilities that could forever change the way we understand the universe. While the scientific community has yet to observe these faster-than-light particles, their potential to reshape our understanding of time, space, and the very nature of reality itself is undeniable. Tachyons are not just a curiosity within the realm of theoretical physics. They represent a profound challenge to the established laws of physics and invite us to rethink the limits of what is possible. The concept of tachyons forces us to confront some of the deepest questions in physics. If tachyons exist, they would directly challenge the foundational principles of special relativity, which tells us that the speed of light is the ultimate speed limit. This would not just be a minor adjustment to our theories, it would require a major reworking of the equations that govern the movement of particles, the flow of time, and the structure of spacetime itself. The very existence of tachyons would prompt us to rethink how we approach the fundamental laws of the universe. One of the most intriguing aspects of tachyons is their relationship with time. The possibility that these particles could exceed the speed of light opens up the tantalizing prospect of time travel. If tachyons can move faster than light, they could, in theory, reverse the flow of time, creating paradoxes and challenges to our understanding of causality. While this may seem like science fiction, the idea that particles can break the time barrier raises important philosophical and scientific questions. Could tachyons allow us to communicate with the past? Could they be used to send information across time, altering the course of events? These possibilities, while speculative, force us to consider a universe where time is not a rigid, unchanging flow, but something far more malleable and dynamic. The potential applications of tachyons extend far beyond the realm of time travel. If these particles exist, they could revolutionize communication, enabling us to transmit information faster than light, breaking the limits of space and time. They could open up new possibilities for instantaneous communication over vast distances, making it possible to send messages across the universe in real time. Such a breakthrough could transform space exploration, allowing astronauts and spacecraft to communicate across unimaginable distances with minimal delay. This would make missions to distant planets, or even interstellar exploration, more feasible and efficient, and could help us better understand the far reaches of the cosmos. Similarly, tachyons could have groundbreaking implications for energy transfer. Current methods of energy transmission are constrained by the limits of the speed of light, which means that energy must travel through conductors, wires, or electromagnetic fields to reach its destination. Tachyons, with their ability to exceed the speed of light, could enable the instantaneous transmission of energy over vast distances, potentially revolutionizing the way we generate, store, and distribute energy. This could lead to more efficient energy systems and could be key to solving global energy challenges, including the development of sustainable and lossless energy grids. Moreover, tachyons could have a profound impact on the future of computing. If they can move faster than light, they could enable data to be transferred and processed at speeds far beyond what current technologies can achieve. Quantum computing, which already leverages the principles of quantum mechanics to outperform classical computers in certain tasks, could benefit from tachyon-based systems, potentially allowing for exponentially faster data processing. The ability to process information at these speeds could unlock new frontiers in artificial intelligence, machine learning, and computational research, creating opportunities for breakthroughs in fields ranging from medicine to climate science. Despite these exciting possibilities, the challenges of detecting and studying tachyons cannot be overstated. The very properties that make tachyons so intriguing, such as their weak interaction with matter and their supposed ability to travel faster than light, also make them extraordinarily difficult to detect. Current experimental methods, which rely on the interactions of particles with electromagnetic fields and other forces, are not equipped to observe tachyons directly. The lack of empirical evidence for tachyons, combined with their potential to violate the laws of causality and relativity, makes them one of the most controversial and elusive topics in modern physics. However, this only adds to their allure, as the search for tachyons pushes the boundaries of what we know about the universe and challenges scientists to explore new ideas and methodologies. Even if tachyons remain purely theoretical, their study has already had a profound impact on the field of physics. The very idea of faster-than-light particles has inspired new theories, new lines of inquiry, and a rethinking of the fundamental principles that govern the universe. The search for tachyons has encouraged physicists to ask deeper questions about the nature of time, space, and energy, and to consider the possibility that the universe operates in ways we have yet to comprehend. Tachyons represent a frontier of scientific discovery that is still unfolding, one that may take decades or even centuries to fully understand. In many ways, tachyons are a symbol of the unknown, the frontier of human knowledge and imagination. They represent a challenge to our current understanding and a reminder that the universe is full of mysteries yet to be solved. Whether they exist or not, the study of tachyons embodies the spirit of scientific exploration, a commitment to pushing the boundaries of what is possible and daring to ask the questions that no one has yet thought to ask. The future of physics, driven by the search for tachyons, holds the potential for groundbreaking discoveries that could forever change the way we understand the cosmos. As we look to the future, it is clear that tachyons will continue to captivate the imagination of scientists and the public alike. Whether we ever observe them directly or not, the quest to understand faster-than-light particles represents a deeper journey into the heart of the universe, challenging us to rethink everything we know about space, time, and reality. In the end, Tachyons may not just be particles that travel faster than light. They may be a window into a new era of scientific discovery, one where the limits of the universe are not as fixed as we once thought.